We want to leverage cheap asynchronous sensors for localization and design a modular system that can fuse these asynchronous measurements. Using pose graph-based optimization, we want to allow for the direct incorporation of measurements without increasing the overall graph complexity. Let's consider a simple example where we have a vehicle with a LiDAR camera and GPS sensor attached. Looking between two LiDAR time instances, we can create a factor graph that has two binary factors from the LiDAR and camera and two unary factors from the GPS. The underlying measurements coming from the sensor odometry packages are pose estimates, which are denoted as diamonds on the timeline. The naive way to construct our factor graph is to convert two sequential LiDAR and camera poses into a binary factor by selecting poses that are close to the same measurement time instant. The issue is that because these pose measurements come in asynchronously, each factor will be a measurement of the state at different time instances. We propose a solution to the asynchronous measurement alignment problem. We look to correct all the incoming pose measurements so that they are aligned to the same time instance. Seen in purple, we propose using linear interpolation between two bounding pose measurements to calculate a corrected measurement pose at the desired time instance. In this case, both the camera and the GPS measurements are shown to be interpolated to match the LiDAR sensor timestamp. Using the graph states and measurement timestamps, we use two time-distant lambdas to interpolate the measurement, equating to a stretching or shrinking of it. In this case, a relative measurement from time 1 to 2 will be interpolated to the state times b and e, where the orientation is interpolated on the SO3 manifold to ensure that it remains valid. Additionally, the original covariance is corrected through covariance propagation for use in graph-based optimization. Now that we can incorporate these low-cost asynchronous sensors into our graph-based estimation, we also want to limit the number of sensors a vehicle has. To this end, we would like to remove the dependency of using high-cost GPS sensors while still allowing for the robot to navigate in the GPS frame of reference for modules such as path planning. We propose a two-part system. The first creates an accurate prior map using a vehicle equipped with an RTK GPS unit. A fleet of lower-cost vehicles can then localize in the GPS frame of reference using this prior map and without the use of an onboard GPS sensor. Poses from LOAM and OrbSlam2 odometry packages are fused with an RTK GPS to generate the 3D point cloud prior map, leveraging the proposed measurement alignment. This prior map allows us to localize in the GPS frame of reference. We apply the proposed method to align the vision measurements to the LiDAR states. To see the improvement due to the proposed interpolation method, we run the GPS-designed system without using the prior map. This shows that if only odometry is used, the proposed method will achieve higher accuracy state estimation. In conclusion, we have presented a general approach to asynchronous measurement alignment for state estimation. We have presented a modular system that allows for GPS-denied localization and demonstrated its ability to perform on an experimental dataset. Finally, we have shown that the proposed interpolation method provided a significant improvement over the naive ignoring of the asynchronous nature of incoming measurements.